Ozone, a crisis and recovery. So what is ozone? Ozone is a highly reactive and powerful oxidant composed of 3 oxygen atoms and plays a very important part in protecting life on Earth. Most ozone is found in the stratosphere between 15 and 50 kilometers above Earth's surface. This thin layer acts like a sunscreen for life on Earth, as it absorbs the most dangerous UV radiation, specifically UVB and UVC. Without it, we'd suffer from higher rates of skin cancer, cataracts, crop damage, and much more. Now, it's important to know there are 2 kinds of ozone. Up in the stratosphere, we have good ozone, the protective shield we just talked about. Now, here in the troposphere, right where we breathe, ozone becomes bad ozone. It's a key ingredient in smog and acts as a harmful air pollutant. It can irritate our lungs and damage plants and trees. So remember, same molecule, very different location and effects. So, how is the ozone layer naturally maintained? It is maintained by a natural cycle driven by sunlight, better known as the Chapman cycle. Here is how it works. First, high energy UVC radiation from the sun splits an oxygen molecule. Second, the single oxygen atom quickly joins with the O2 molecules to form ozone. Third, when ozone absorbs UVB radiation, it breaks apart again, and then the cycle repeats. In addition, in the stratosphere exists natural ozone-depleting substances such as nitrous oxide, peroxides, and halogens, which can make up about 1 to 2% of natural ozone depletion, with the remaining being anthropogenic causes. The natural cycle we just saw is incredibly effective at protecting us, but it can be disrupted. Human-made chemicals, especially CFCs, once used in refrigerators and aerosols, can release chlorine and bromine that catalytically destroys ozone. Even so, the natural formation and depletion processes continue to operate in the background. The anthropogenic production of ozone-depleting substances, CFCs, HCFCs, and methyl bromides break down under solar radiation in the stratosphere, releasing chlorine and bromine radicals. One of these radicals can destroy thousands of ozone molecules in a catalytic cycle. As you can see, anthropogenic emissions of these substances can have a detrimental effect on the ozone layer.
The ozone hole is a region with extremely low ozone concentration in the stratosphere over Antarctica. It is called a hole, but it does not mean ozone is completely gone. Instead, it means the ozone level becomes unusually low compared with normal conditions. NASA defines the ozone hole as an area where total ozone falls to 220 Dobson units or lower. A Dobson unit is a way to measure the total amount of ozone in a vertical column of the air. Ozone destruction happens most strongly over Antarctica because the stratosphere there becomes extremely cold during the long polar winter. A strong circular wind system called the polar vortex traps cold air over the continent. Under these cold conditions, polar stratospheric clouds form, and important chemical reactions happen on the surfaces of those cloud particles. These reactions convert inactive chlorine into more reactive forms. Then, when sunlight returns in the Antarctica spring, ultraviolet radiation breaks these components apart and release reactive chlorine, which rapidly destroy ozone. So, the ozone hole is one of the clearest examples of how human-produced chemicals can cause large-scale changes in the atmosphere. When we look at the global trend of ozone destruction, the story is not only about damage. It is also about international action and gradual recovery. The most important response was the Montreal Protocol, adopted in 1987. This treaty regulates the production and consumption of ozone-depleting substances, including CFCs and other harmful chemicals. It is one of the very rare environmental treaties to achieve universal ratification, meaning every country agreed to participate. The treaty also includes trade controls, annual data reporting, and national licensing system to control the import and export of ozone-depleting substances. Another important part of this global effort is the Multilateral Fund, which was created to help developing countries follow the treaty. This fund provides financial and technical support for industrial conversion, training, and capacity building. In other words, the global response was not just about making rules, but also about helping countries actually meet them. Because of these actions, the amount of ozone-depleting chemicals in the atmosphere has been decreasing. A useful scientific indicator for this is the NOAA Ozone-Depleting Gas Index, or ODGI. This index tracks the amount of reactive halogens, mainly chlorine and bromine, in the atmosphere. On this scale, 100 represents the peak level of ozone-depleting halogens, and 0 represents the 1980 level, which is used as a recovery benchmark. The ODGI shows that recovery is happening, but not all at the same speed everywhere. In the mid-latitudes, the ODGI value at the beginning of 2024 was 45.3, which means the halogen burden had decreased by about 55% from its peak. Recovery to the 1980 benchmark there is projected to happen around 2045. In Antarctica, recovery is slower because the air is older and mixing processes are more complex. At the beginning of 2024, the Antarctic ODGI value was 71.6, meaning only a 28% decrease from the peak. And recovery is projected around 2070 based on NOAA index. More broadly, the World Meteorological Organization reports that if current policy stays in place, ozone is expected to return to 1980 levels by around 2040 for most of the world, 2045 in the Arctic, and 2066 over Antarctica. This shows that the ozone layer is recovering, but very slowly. It also shows that even after emissions are reduced, the atmosphere needs decades to respond. So, the global trend can be summarized like this. Human activity caused serious ozone destruction through chlorine and bromine containing chemicals, but international cooperation greatly reduced those emissions. And now, the ozone layer is on a long path toward recovery. This makes the ozone story one of the best examples of successful global environmental policy.
In all, ozone is an important part to our life on Earth. It has its own natural cycle of depletion and replenishment, and human-manufactured chemicals threw off its balance. The main threat is still ozone-depleting substances, but major changes have been made to reduce depletion. Manufacturing of CFCs was banned, cutting 99% of ozone-depleting substances globally. Safer refrigerant alternatives with lower ozone depletion potential and new aerosol propellants were developed. An example of these policies can be seen in farming emissions in Canada. Nitrous oxide and methyl bromide emissions are being cut by changing fertilizer and fumigation practices. A 30% reduction target from 2020 levels by 2030 is in place. As we can see, the real atmospheric data from the ODGI graph confirms progress. Mid-latitudes are already halfway to the 1980s levels, while Antarctica lags. Slight rises in some halons show we must keep monitoring. The phase-outs work. The data proves it.